Okay, let's start class. In this class, we will look at how the distribution of charge density in the depletion layer changes when a forward bias is applied, and how the electric field, potential, and energy change from this. Next, we will examine the carrier concentration distribution and how the quasi-Fermi energy EFP and EFN for holes and electrons change. Based on this, we will derive an ideal current voltage relationship based on the diffusion of minority carriers. A built-in potential VBI is formed in depletion layer. So here will be VBI. So VBI is formed in the depletion layer of the p-n junction in thermal equilibrium. When a forward bias is applied to the p-n junction, where will this voltage mainly be applied? As before, the neutral region outside the depletion layer has a high carrier concentration, resulting in very high conductivity, and conversely, a very low resistivity. As a result, the voltage drop V equal IR is almost zero or extremely small and can be ignored. Therefore, most of the applied voltage Vf is applied to this depletion layer. Since the electric field induced by the applied voltage has the opposite direction to the electric field caused by the built-in potential, it lowers VBI, right? So as a result, a smaller electric field exists from the N-type to the P-type in the depletion layer. If the electric field decrease the width W of the depletion layer also decrease because the amount of charge decrease. Since a positive voltage is applied to the P side by the forward bias, of course, the majority carriers are pushed further in the plus X direction, and the acceptor ions forming charge neutrality with the holes disappear from the space. At the same time, negative voltage is applied to the N side, so electrons, the majority carrier, move in the minus X direction, and donor ions disappear from space. Therefore, the balance between the diffusion force and the electric field force in thermal equilibrium is broken. The electric field force preventing the diffusion of the majority carrier across the depletion layer is reduced, so electrons in the N region cross the depletion layer to the P side, and holes in the P region also pass the N side. As long as bias voltage is supplied, the injection of the majority carrier across the depletion layer continues, so current flows in the PN junction. This bias condition is called forward bias. At this time, the width of the depletion layer can be obtained as follows by substituting VBI minus VF instead of VBI. That is, as the forward bias increase, as the forward bias increase, the overall depletion layer width is going to decrease. The following figure compares between forward bias and thermal equilibrium. Within the depletion layer region, the, the magnitude of the electric field decrease as the forward bias increase. As we saw last class, the electric field is a linear function across the depletion layer. As the forward bias increase, the electric field decrease because XP and XN are decreased. And as in the case of reverse bias, the maximum electric field in the PN junction can be expressed as the width of the depletion layer. As the width of the depletion layer decrease, the electric field decrease, and at the same time, the potential also decrease to VBI minus VF, so that the energy barrier is lowered to VBI minus VF when electrons existing in the conduction band of N region proceed to the P region. At equilibrium, the concentration of electrons that are minority carriers in the P region is looking like in this way. So the larger this gap, so this would be A, right? So the larger this gap, the smaller the concentration. On the other hand, the electron concentration in this N region looking like in this way, and the concentration increase as this energy gap. So this would be B, right? This gap. So therefore, The ratio of electron concentration in the two regions can be summarized as follows. In other words, at a position where the energy concentration is as low as VBI, the electron concentration increase by exponential EVBI over kT times. So after applying forward bias, the electron concentration can be expressed using the electron's quasi-Fermi energy. In x equal minus xp, if n1, if n1 is the electron concentration of the minority carrier in the p region, it is equal to this one, and the larger this energy gap, the smaller electron concentration. On the other hand, N2, N2 is the electron concentration of the majority carrier at x equal xn. N2 becomes this one, and the smaller this energy gap, the higher the electron concentration, right? So at this time, since the ratio of N1 and N2 is as follows, and N2 is equal to N, N, and I mean, N2 is equal to N and 0. It can be expressed as follows. So here, N2 is equal to N0 is assumed, but this relationship is valid when we assuming low level induction, where the concentration of the injected minority carrier is much smaller than the concentration of the existing majority carrier. That is, when the concentration of holes injected from the P-type to the N region due to the forward bias, due to the forward bias is much smaller than the electron concentration of the original N region. The concentration of excess electrons, I mean, this much excess electrons gathered near the interface to achieve charge neutrality with these injected holes is very small compared to N0. So this one, N2 minus N0 is almost 0. So which is the electron concentration in equilibrium, so it can be ignored. Similarly, the concentration P1 of minority carrier holes at x equal xn can also be defined as in this way. After all, when a forward bias is applied, each region acts as a continuous source of minority carriers for the other region. Crossing the junction, the majority carrier is injected to the other side, looking like in this way, and accumulates, accumulates in this way, right? They are accumulates as excess minority carrier, and the injected excess minority carrier diffused, diffused deep into each region and recombines. When they are diffused to here, they are going to recombine. They are going to recombine and disappear. This would be same here. And they are going to diffuse. They are recombine with electrons and disappear, right? Then let's find the concentration distribution of excess carrier in the steady state. You may remember the ambipolar transmission equation for the excess carriers. These are the excess minority carriers. These are the excess minority carrier concentration, delta MP and delta PN, and represents the difference between the total minority carrier concentration and the thermal equilibrium minority carrier concentration, which means which means delta MP is equal to MP minus NP0. So in the neutral region outside the depletion layer, the carrier concentration is high and the conductivity is very high, so the resistivity is very small. As a result, the voltage drop, the voltage drop is almost zero. Therefore, E equal zero and G prime equals zero in the neutral region. And in the steady state, it goes to zero. So the ambipolar transmission equation can be summarized, as follows. And the relationship obtained in the previous slide can be used as a boundary condition. At this time, it is assumed that the length of the neutral region is much longer than the diffusion length of the minority carriers, and the concentration of excess minority carriers at a distance from the depletion layer is regarded as zero. This structure is called a long PN junction diode. Now, if the general solution of the equation is obtained, and boundary conditions are substituted, the following form. The following form can be finally obtained. The excess minority carrier concentration decrease decrease exponentially with distance from the junction, and finally reach a summer equilibrium. So if we graph this, we get the same result as before. Then let's take a closer look at the IV characteristics of PN junction diodes. The ideal IV relationship can be derived from the following four basic assumptions. First, depletion layer approximation. The depletion layer has a stepped boundary. Outside the depletion layer, the semiconductor is neutral. Second, applying the Maxwell-Boltzmann approximation to the carrier distribution. Third one, low-level injection. So do you remember? It means that concentration of excess carrier is much smaller than the concentration of the majority carrier. Final one, the total current is constant over the entire region of the PN junction. And the current of each electron and hole is a continuous function and is constant throughout the depletion layer. In general, since the width of the depletion layer is very narrow, it is reasonable to assume that electron and hole currents do not change as they pass through this region. So let's take a look at the current density J, when forward bias is applied to the PN junction. There are two types of particles that contribute to current, holes and electrons, and two types of movement mechanisms, drift and diffusion. We know that this one is drift and this one is diffusion, right? When they are combined, a total of four current compositions. At this time, to calculate the total current density, the electron current density and the hole current density are summed at an arbitrary point x equal 0. So when x is 0, Jn is equal to the current density of minority carrier electrons injected from N-type to P-type across the depletion layer. So is the current density of holes. The reason for this is that respective electron and hole currents are continuous functions and are assumed to be constant throughout the depletion layer. So the total current is equal to the sum of the current densities of the minority carriers in each region, which is constant across the junction. First, let's find let's find Jn minus xp. The diffusion current density of minority carrier, in this case electrons, at x equal minus xp can be written as follow. Here, the constant value npx is obtained by adding the excess carrier to np0. And since constant doping is assumed, the concentration np0 has a constant value. So the expression becomes looks like in this way. Substituting here the excess minority carrier equation from the previous slide, we get this result. And similarly, the whole current density in n-type is obtained as follows. At this time, it can be seen that both current densities have the same direction as the current due to the forward bias plus x direction. Now, if you add up, if you add up all the obtained values, you can get the total current density. This current density is constant over the entire of the PN junction diode, the ideal IV relationship. At this time, in the case of reverse bias, minus VR, minus VR can be applied as it is instead of VF. And if JS, JS is as defined as this one, JS. If JS is defined as this one, the final ideal diode equation can be obtained. If you draw this as a graph, it is as follows. And you can also check the symbols and standard of currents and voltage. That is, as you can see, the IV characteristics of the PN junction diode have an asymmetric rectifying characteristics. Until now, we have been interested in the diffuse current density of minority carriers in the boundary regions on both sides of the depletion layer. But now, let's look at the change in current density by minority carriers in each P and N region. In the case of low level injection, the motion of excess carriers injected by the forward bias is governed by excess minority carriers based on the ambipolar transport theory. Since the electric field in the neutral region is almost zero, the drift current is negligible. That is, the current density of minority carrier in each region is equal to electron diffusion current density J N X for p-type and JPX for n-type. So we find the following exponential decay within each region. And since the total current flowing through the PN junction is constant, the current density of the majority carrier is obtained in this way, right? It can be obtained this way by subtracting the diffusion current density of the minority carrier from the total current density J. In this situation, if the forward bias is several times higher than the thermal voltage, minus 1 in equation can be ignored. At this time, Ln, J, and Vf have the following relationship. And since the slope is E over kT, the temperature T and Js can be obtained from this graph. Conversely, if the voltage is reverse biased by several times the thermal voltage kT over E, then the reverse bias current density becomes almost constant regardless of the reverse voltage, and Js at this time is called reverse saturation current density. So this Js, this Js is a function of summer equilibrium minority carrier concentration. So Js is proportional to Ni squared. As you can see, the Ni squared is function that is sensitive to temperature. Sensitive to temperature, not only the Nc and Nv terms proportional to the 3 over 2 square, but also the exponential function term. In addition to the temperature dependence of Js, forward bias currents also has a temperature dependence, right? It also has a temperature dependence. Therefore, with the constant voltage applied, as the temperature increase, the diode current increase. Conversely, the forward bias voltage required to obtain the same diode current decrease with increasing temperature. This change in IV characteristic with temperature can be utilized to measure temperature. Let's take an example. A forward bias 0.6 volt was applied to the silicon PN junction at T equals 300 Kelvin. at this time, when the temperature increased to 310 Kelvin, we will find the change in Js and current density J. We know that the river saturation current density Js looking like in this way, and Ni squared and Nc and Nv, they are proportional to temperature, right? So we know that this Js is proportional to T cubed exponential minus Eg over Kt. Here, we are just comparing the case of 310 Kelvin and 300 Kelvin. It can be seen that Js increased about 4 times when the temperature rise by 10 K. And next, we know that the forward bias, the forward bias is proportional to T cubed exponential EVF minus EG over KT. Since there is an exponential EVF over KT term in addition to this JS. Therefore, when comparing 310 Kelvin and 300 Kelvin, it can be seen that when the temperature increased by 10K, the forward bias doubles. As a result, it can be seen that the forward bias is less sensitive than the reverse saturation current density. 그래서 이렇게 오늘 수업에서는 이 forward bias에서 PN 정션의 전기적인 특성에 대해서 해석해보고 PN 정션 다이오드의 이상적인 전류 전압 특성에 대해 살펴봤습니다. 다음 시간에는 여기에 더해서 뭐 리컨비네이션 그리고 제너레이션이 발생할 때의 전류 전압 특성 그리고 확산 커패시턴스에 대해 알아보는 시간을 가지도록 하겠습니다. 그러면 수업 여기서 마치도록 하겠습니다. 감사합니다.